Okay, this is Kinetics short answer review. Make sure you have your reference tables close by, maybe a calculator. Base your answer on the following question on the information below and your knowledge of chemistry. In a lab activity, each of 4 different masses of KNO3, potassium nitrate, is placed in a separate test tube that contains 10 grams of water at 25 degrees Celsius. When each sample is first placed in water, the temperature of the mixture decreases. The mixture in each test tube is then stirred while it's heated in a hot water bath until all of the KNO3 solid is dissolved, so we're making them homogeneous mixtures. The contents of each test tubes are then cooled to the temperature at which KNO3 crystals first reappear. The procedure is repeated until recrystallization temperatures for each mixture are consistent as shown below. All right, so that's a lot of information. The data table can kind of make it concise for us. So we see 4 different mixtures, different masses of the salt, the KNO3. Notice the same amount of water, and then what temperature does it take to recrystallize? Then it says, based on table I, explain why there is a decrease in temperature when the KNO3 was first dissolved in water. Okay, so we need to go to table I. That's not what I wanted. So here we are, table I. And I have already highlighted KNO3. So this is KNO3 solid. It's the H2O over the reaction arrow means dissolving, and it becomes K plus ions and NO3 minus ions in solution, AQ, aqueous. And it says positive 34.89 kilojoules, delta H. What does that mean? It says the delta H values are based on molar quantities represented in the equation. Minus sign indicates exothermic. We don't have a minus sign. We have a positive sign, which means it's endothermic. And that should make sense to us because based on table I, decrease in temperature. So KNO3 solid, when dissolved, undergoes an endothermic process. And when something is endothermic, that's going to be absorbing heat. So heat is absorbed and temperature would thus decrease. According to the answer key, it says the solution would decrease because the dissolving of KNO3 is endothermic. The heated solution is positive. Delta H is positive 34.89, requiring energy to dissolve. Yeah, so using table I, you find out that it's endothermic, and then you just need to relate it to why the temperature goes down. Base your answer on the following question below. Carbon monoxide is a toxic gas found in automobile exhaust. The concentration of CO gas can be decreased by using a catalyst in the reaction between CO and O2. The reaction below is, here we go. Catalyst over the reaction arrow. We should remember that catalysts speed up the rate of the reaction by decreasing activation energy and providing an alternate reaction pathway. It does not participate in the reaction. It just speeds it up. On the labeled axes below, draw the potential energy curve for the whatever. All right, so this just says energy is on the right side, the product side, so this means it's an exothermic reaction. Notice we have no actual numeric values on the X or Y, so we don't have to be super specific. We just need to draw an exothermic potential energy diagram. So you know exothermic starts flat, raises up to who cares, comes down, but it has to be below where you started. So exothermic, this has to be below this. So if you were to figure out delta H, it would be a negative. But we don't have to. That's all you got to do. 3 and 4 are the same thing. The compounds KNO3 and NaNO3 are soluble in water. Explain why the total thermal energy containing 22.2 grams NaNO3 dissolved in 200 grams of water at 20 degrees Celsius is greater than the total thermal energy of a sample of 11.1 grams of NaNO3 dissolved in 100 grams of water. Sorry, I just need a sip of coffee. So we have double the mass. So the mass has increased, which means there is more heat because dissolving is a talking about heat process, And we can use, all of the heat formulas, Q equals MC delta T, Q equals MHF, Q equals MHV. All of these require mass. So again, we don't need these formulas right now, so we don't need to include them. But just know that mass is, it's proportional to heat energy. So why is the heat energy greater with that? Mass is increased. There are an increased number of particles. Yeah. So it doesn't matter that the temperature is the same because temperature and heat are different. So because the mass is increased and there's a greater number of particles, therefore there's a greater heat value. What does the answer key say? Both samples are at 20 degrees Celsius. The larger sample has more matter. Larger sample has twice as many particles. Total thermal energy is directly proportional to the masses. You have something like that. Okay, compare the entropy of 30 grams solid CaNO3 at 20 with the entropy of 30 grams CaNO3 dissolved in water. So we're basically saying, what's the difference in entropy? Sorry, I got my washing machine going. Solid versus NO3 aqueous. So again, a solid would be really tightly packed. Show it tightly packed. And then aqueous, we're going to have water molecules, which it's hard for me to draw these. It's not beautiful. But they're going to be evenly distributed amongst, So this on the right, aqueous, has more entropy, more randomness, more chaos, more disorder. All those words are synonyms than the solid. So when it says compare, you just say the aqueous, the solution has more entropy than the solid. Or you could say the solid has less entropy than the aqueous. Okay, so 5 and 6. At 550 degrees Celsius, 1 mole of CO2 and 1 mole of H2 are placed in a 1 liter reaction vessel. Substances react to form carbon monoxide and water. Changes in the concentration of reactants and the concentration of the products are shown below. Okay, so you see we have time on the X, then we have concentration in moles per liter, molarity could be. And so notice what happens over time. It looks like the concentration will decrease for reactants, increase for products, until eventually they just flatline, which means stay the same. What can be concluded from the graph about the concentration of reactants and products between time T1 and D2? Concentrations are constant. Notice they're not equal. The product is at 0.27, the reactant is at 0.73. That's not the same, but notice how both of them don't change. So concentrations are constant. So con. I would leave it at that. Determine the change in concentration of CO2 between T0 and T1. Well, change in it's always T fine. Well, I say T. It's because it's usually, whoa, what did I do? Sorry about that. Usually time, but it's just, we'll just say T1 minus T0, the change. So T1, this is the CO2 gas. T1 is 0.73. T0 is 1. Why did I even do math on that? Okay. Oh. Wait, sorry. I did T0 and T1. Oh, oops. I did it backwards. Sorry. Because it told me how to do it. Don't listen to me. I made a mistake. It said T0 and T1. So start at T0, which is 1. Then we're at 0.73. So then you get a difference of 0.27. So sorry about that. I was trying to do T final minus T initial, and we just had to go from where you start and where you end. Now, you should really have some units, so that's moles per liter, which you get from here. Washing machine's going crazy. Okay. A phase change for carbon dioxide occurs spontaneously at 20 degrees Celsius, 1 atmosphere. Here's the reaction. Draw at least 5 molecules in the box to represent CO2 after the phase change. So CO2 after the phase change is in the gas form. And I don't even need to draw it like this because it asked me to just draw a white circle. So how do I draw 5 molecules of a gas? Show them taking up all the space. Okay, and it doesn't matter, it doesn't have to look exactly like mine, but they need to be taking up the whole space, not grouped together. The equilibrium equation below is related to the manufacture of a bleaching solution. In this equation, Cl aqueous means that the chloride ions are surrounded by water molecules. Explain in terms of collision theory why increasing the concentration of Cl gas increases the concentration of OCl, which should not be a capital L, in this system. Okay, so when you increase the concentration, my washing machine, you're going to increase, obviously, number of particles. And when you have more particles, that's going to increase collisions, which means increasing the formation of products. Yep, something like that. Increase concentration, increase collision. You got to talk about collisions because it says collision theory. And so it'll produce more of the products here. All right. It says to graph. Do I really have to graph for you? Especially because it's so small. I'm just going to say, I guess I could. When we're looking on the axis, let's see, reaction time. I don't know. We could go by 5s. Can I make this bigger? Will it stay there? 60, 70. Okay, so those are our reaction times. Trial 1 is at 11 with a concentration of 0.20. 0.20, 11. So be like right there. Trial 2, 0.015, and that's 14. Okay. 0.010 is at 23. Oh, it should be maybe a little bit lower than that. And 0.005 is at 58. Something like that. Okay. So it says plot the points, circle and connect the plots, points like that. So, again, you don't have a data point here, so don't do anything with that. Certainly don't bring it to 0. You wouldn't have a straight edge on the regents. So you could use, if you wanted, you could use a straight edge of like your paper, like an additional piece of paper, or you could just kind of eyeball it like that. Okay, so there we go. There's our graph. And then the last question says, state the effect of concentration of the reactant on the rate of chemical reaction. So concentration is increasing as reaction time is decreasing. So as concentration increases, rate decreases. You could say it's an inverse if you want. All right. I didn't know. Okay. Let me know if you have any more questions. Please reach out. Thank you.